Now I want to show you an example of how to solve a conservation of angular momentum problem. So we're going to do the classic, which is the ice skater trick. I'm sure that in ice skating and many other sports as well, there's the idea that like if you tuck in, your body will rotate faster, and if you extend outwards, your body will rotate slower, which is frequently used for doing spins in ice skating and diving and gymnastics and many other things. There's these concepts of like tucking in. So why does that work? Our little kind of cartoon version of that example is one that you can easily do a demonstration of, which is, imagine in this case you're sitting in a chair that can swivel around in circles, and you get yourself swiveling at an angular velocity of 2 radians per second, and now you stick out your arms and effectively increase your radius, so to speak, increase your moment of inertia, and that's going to change your angular velocity, because conservation of angular velocity says that your moment of inertia times angular velocity has to remain constant. So if you change your moment of inertia, you'll also change your angular velocity. So in this case, just to keep this problem simple and doable, we're going to assume that the person's body is approximately a solid cylinder. So we'll assume that before they stick their arms out, they're a solid cylinder of 40 centimeter radius, and after they stick their arms out, they're a solid cylinder of 50 centimeter radius, just to pick some numbers. Okay, so first step is to realize that you have conservation of angular momentum in this problem, and then you bring the conservation of momentum framework to bear. So the first thing you need to do is identify and draw the initial state and the final state. Now this is going to look a little bit different from how it looks in linear momentum conservation, but it's really the exact same process. So in this case, before and after, the initial and final states are just a cylinder, but the cylinder has gotten bigger. So let's say it's rotating counterclockwise so that everything's positive. So it's initially rotating at 2 radians per second, and the radius here is 0.4 meters. And in the final state here, it's rotating at an unknown final angular velocity with a radius of 0.5 meters. So in this case, there's not like a collision in the same sense that there is in most of the conservation of linear momentum problems we solve, but you can still apply the same procedure. So we've drawn our initial picture, we've drawn our final picture. The next step is to write down what is the momentum in the initial picture and what is the momentum in the final picture. But in this case, it's angular momentum. So in the back of my mind, everything's a solid cylinder here. So the formula I have in the back of my mind for all of this is the formula for a solid cylinder, that I equals 1/2 mr squared. So that's going to be how we calculate our I, and then the omegas, of course, are just written out here. So let me do this step by step. For the initial picture here, we're going to apply the cylinder formula. So 1/2 times the mass is given in the question here as 100 kilograms. It's a high mass, but just to pick round numbers. And we've got a radius of 0.4 meters. So that's your R. So there's my moment of inertia. Let me just crunch the numbers just to make for a little bit less writing. And I get here 8 kilogram meter square. So that's the initial moment of inertia. Now we're going to have a different final moment of inertia. Same formula, but this time it's 100 kilogram mass with a 50 centimeter radius. So now we're going to have 0.5 times 100 times 0.5 squared, which gives 12.5. So you'll notice that, as expected, the moment of inertia went up, because the moment of inertia will go up if you move the mass further from the axis of rotation. Then I also need to think about my angular velocity. So the initial angular velocity is, of course, 2. And the final angular velocity is my unknown variable. So I'm just calling it omega. So now I've got all the pieces in place. Now I can calculate the angular momentum, and I'm running out of space here, so let me kind of do this all at once. I want to set the initial angular momentum equal to the final angular momentum, and that means I'm using the definition I times omega in the initial state equals I times omega in the final state. So here we have, I'm going to drop the units because I don't have a lot of space here. We have 8 times 2 on this side. And over here we have 12.5 times our variable omega. So that means we're going to have 16 divided by 12.5, which is 1.28 radians per second. And you will notice that compared to the initial speed of 2, the cylinder slowed down, which is consistent with what you would expect if you know anything about these tricks in sports. When you extend yourself outwards, it slows down your rotation. When you tuck yourself in, it speeds up your rotation. Okay. But notice, so this is interesting for everyday life, but it's also a good illustration of how you apply the conservation of momentum procedure to a new situation.